start the first session. So yeah, welcome back, everybody. In the first session, we will watch 3 videos. One is about the simulated utilization analysis. Then we'll have a video about doing memory management for in-memory databases on a composable system prototype. And lastly, we will learn something about lessons from actually running a composable systems in a productive environment. So the videos pretty much introduce themselves and all the authors, so not more words needed. I hope you can see the screen. So and we'll also hear the sound in a second. And well, yeah, let's start with the first submission.
Hi, I'm Mark Taubenblatt, and I'm going to be talking to you about our work on quantifying composable data center utilization. I'd like to thank the organizing committee for including our work in this first COMPSYS workshop, and also note that I recently retired from IBM, and my colleague Asr Tantawi will be answering questions after this recorded talk. I'd also like to direct you to our paper, which has significantly more detail than I'll be able to cover in this talk. So one of the goals of our work was to quantify the utilization advantage of composable systems. Utilization is often touted as one of the big advantages of composable systems, but in order to determine the actual amount, we needed to develop some simulations that would let us do that and also understand the impact of the size of the composable resource pool. All this is really needed because composable systems are not free. The network that ties the composable resources together in a low latency, high bandwidth network are really going to cost some money. So we need to understand whether the advantages of composable systems actually offset the additional cost of the hardware. So in order to do this, we developed a discrete event simulation model, which I will discuss, and we analyzed 3 different scenarios. A very simple multi-server loss queue model, which highlights the issue of fragmentation in data centers. And we also developed 2 more realistic scenarios, a mixed memory size demand model and a mixed ratio CPU-GPU demand model. We were able to quantify the utilization advantage in several scenarios, showing that composable systems can provide many tens of % utilization advantage over more conventional hardware deployments. And we also found that the size of the composable resource pool needed to be at least 8x the size of the largest VSI placed in the composable pool. The cloud service model, which we use to develop our simulation platform, consists of a data center with various heterogeneous resources such as CPU and memory, as shown by the yellow boxes, an incoming request stream for these resources, which is heterogeneous in nature, has a probabilistic mix of requests and also probabilistic arrival times. As these requests come in, a placement algorithm determines whether there's room in the data center to accommodate these or simply blocks them with a blocking probability that we assess from the simulation. This blocking probability is highly correlated to the queuing time if one chooses to use queues, but we decided that that was an additional complexity that would require queuing policies and therefore simply use the blocking probability as a surrogate for queuing. Once the jobs are finished in the data center, then they move on to free up the space and additional jobs can be placed. I should also note just the example of stranded CPUs up in the upper right corner where workloads come in with various CPU and memory requests, and sometimes the node fills up because of the nature of varying ratios of those requests and leaves a certain amount of resource stranded. And that's the issue that we're trying to address with composability. So we experimented with 3 scenarios. The first scenario was simply a VSI which fits in its entirety on a single server. This highlights the issue of fragmentation in data centers. The issue here is that as we include more and more heterogeneous types of resources in data centers, such as GPUs and AI chips and other various FPGAs and other various resources in different ratios, it creates more and more types of drawers and workloads that need to be run only on those types of drawers. That essentially makes your data center partitioned into a lot smaller pieces, and that has a very significant impact, as we'll see. The next 2 scenarios involve a mixed memory request where we have 4 different memory sizes and 2 different workload request probability scenarios. In this scenario, we not only looked at different memories, how to fit different memory sizes, but also what happens when you have predicted a different request probability in the future and it doesn't come true. And the last one, we explore the issue of trying to accommodate different ratios of CPU to GPU, as many workloads require different ratios for optimal performance. So the multi-server loss queuing model is based on our simulation. And a good example of this is for in-memory databases where data centers deploy ultra-high memory nodes that are only usable for these in-memory databases. And so essentially the number of those deployed is the number of high in-memory database requests that can be accommodated. We derived a coefficient of variation, which is the standard deviation of the mean based on the Google data set that is available publicly, as an example of what might find in a data center. And what we see here is on the chart is the utilization on the x-axis and the blocking probability on the y-axis. And we chose, for the purposes of our work, a 1% blocking probability, a relatively low blocking probability, assuming that we don't want to lose customers and we don't want to have queues. And here we see that for a very small deployment of, say, like 32 and n of 32 nodes, we see that the blocking probability of 1% indicates a utilization of only 45%, relatively low. On the other hand, if you have a relatively large data center of 1,024 nodes, we see that the utilization can be well over 90%. And so what this clearly shows is that for relatively small data centers, due to the variability in the arrival times and lifetimes, that the utilization can be really quite low in this situation. And I do want to emphasize that small data centers are quite important these days, whether for edge deployments or for regulatory requirements such as in-country financial and medical databases need to be kept within country. This sort of speaks to more and more small data centers. And so while the mega data centers may not have so much of an issue here, these small data centers certainly will. So the first example showing here with the mixed memory scenario, I draw your attention to the table 1, where we determined 4 different types of memory requests: the small, medium, large, which could be HPC or in-memory database, and the ultra-high memory, which could be an in-memory database. We explored 2 different scenarios: a high database market and a low database market. And note that the ratios of resources are very different for those 2 scenarios. And I just want to emphasize also that if one deploys the wrong ratio of resources, whether conventional or composable, and the market comes in with a different ratio, you're going to have stranded resources. And so it's really important to try to get that right. And we'll see in some of the work here that composable actually does very well when the resources are not as predicted. Table 2 shows the hardware deployed for composable systems. We tried to come up with drawer sizes that were reasonable, a pod size that we thought was reasonable to connect. We determined the relative costs based on Google instance pricing, and tried to determine ratios that were similar to the ones in the demand in table 1. And then for conventional, similarly, we determined 3 types of drawers that could be used, and allocated those drawer types based on the numbers that would be needed to meet the demand percentages that we were seeing. And we simulated 8 combinations, 2 demand probabilities, 2 hardware deployments, and 2 system types. For the composable systems, we additionally compared the composable pool sizes by factoring the pod into multiple various smaller composable pools. So here we show the results in the upper right. We see that the blocking probability based on the load factor, and we see that, for example, the black curves for an n equal 1, which is the largest composable size, the blocking probability allows a load of 85%, whereas for the smallest composable size, it only allows a load of 63%. And then we go down to the chart below and pick off the utilization based on those load factors and find that for the largest composable size, it's 80% CPU and 85% memory. And for the smallest composable size, only 61% and 63% correspondingly. And then on the left-hand little chart there, you see that most of the advantage of composable is gained within about 8x composable size. So that's where that number comes from. And then we did this for all of the scenarios, and we see that in every case, the composable is better than the conventional. In particular, for the low database, low hardware, we see that it does quite a bit better when when the UHM kind of requests are much rarer. Then composable really is much more able to accommodate those than conventional. And we also see that it does much better when the opposite market is obtained from the hardware that was anticipated. The next example is the mixed CPU GPU scenario, where again we chose 6 different ratios of CPU to GPU and analyzed the situation here. We find for the composable that we were able to achieve in the low 70s, but for conventional, on the next chart, you'll see that there aren't really any good ways to deploy for a conventional, because if one picks a single ratio, then the other ratios are going to have a much harder time, are going to leave a lot more stranded resources. And so one really needs to deploy 6 different types of drawers. The small drawers, the small instances cannot be allowed on the large instance drawers because they would jam them for the large instances. And so one ends up with 6 different drawers with very low numbers, as one sees for the total via size accommodated. And if we go back to our original multi-server model, we see that those numbers are very low, some in the 30s, some 17, 12, and those are going to correspond to very low utilizations. So in summary, we see that increasing heterogeneity in data centers is going to cause fragmentation. It's going to have a very strong impact, and the impact is going to be much more significant for smaller data centers. We see the composable systems can have a 10 to 50% potential utilization advantage, and that a very modest sized composable system can also accommodate a very large range of CPU to GPU ratios, giving us around 72% utilization, whereas a conventional will be well under 50%. And cited in the paper is some previous work where we showed that somewhere in the 25% utilization could actually financially offset the complete cost of the network in the composable system, and therefore that's a really good break-even point. Thank you for your attention.
All right, perhaps first, thank the authors, and then stage is open for questions. So perhaps I start with one question, and that is, having composable infrastructure most likely comes with a performance penalty, right? You have now an interconnect, which could add latency, reduce bandwidth to the resources which are disaggregated. Do you have that in your model, or would it be hard to add it into your model if you have not considered it yet?
It could potentially be added, but it's a good question and completely ignored for this model. And part of our assumption is based on some internal work, not yet published, that we would be using a very high performance backplane, and that's part of the cost analysis, that you would be spending a lot more money on higher bandwidth, low latency interconnection that would partially offset that. Obviously, you're not going to get down to the types of latencies between CPU and memory that you'd have in the same node, but we believe there's also some ways, through software to mitigate those latencies. So yes, there will probably be some degradation, but we're hoping that for most workloads that would actually be mitigatable and not be too much of a factor.
You actually assumed, looking at the presentation that we saw earlier from Paul, where he had, made the distinction between the two types of disaggregation, like the full disaggregation and I think it was the partial disaggregation. And which of those two did you assume in your analysis?
So what we tried to do, and that was, I had to go through it fairly fast, but I recommend reading the paper. But we had looked at the composable systems, and we broke it into where n equals 1. That was one large pod. So in the up to maybe 256 drawers worth of composable, and then we broke that all the way down to 256 separate drawers. So essentially not composable. And looked at the difference between those ranges. And so what we found is that it needed, say in that UHM kind of situation, where one drawer would be occupied by one UHM instance, that you needed the composable pool to be about 8x to get most of the advantage. So that and then the other situation that I didn't talk about in the talk was when we had the very low demand for UHM kind of instances. There it seemed to improve all the way up to the single pool of over 200 drawers. So depending on what you're really looking at, it looked like in a lot of cases maybe a relatively small composable pool could give you a lot of advantage, but in some cases you might, in particular where the very large instances were very rare, it might do you good to go a few times more.
I think this also fits with what Paul was mentioning, right? If you share the memory, or it is sufficient to share memory among two systems, right? You do not have to share it, among the whole cluster to gain a lot of benefit for the applications.
That, yeah, it looked like, I wouldn't say 2 was probably too small for what this sort of UHM kind of situation we were looking at, but you may indeed get a lot of advantage just from smaller composable systems, which of course makes the cost go down. You only need one stage of switching network. It certainly has its benefits if we can get away with it. And that was part of the interest in looking at that is if you have to develop a multi-stage, many rack composable system, the cost is obviously going to go up quite a bit.
Right. So are there other questions? If not, I would say thank you again for the authors for answering the questions, and looking at the time, then we probably proceed to the next submission. And for that, let me show you my screen again. Go to this one here.
Hello, everyone. I'm Marcel Weißguth, a PhD student at the Hasso-Plattner Institute in Potsdam, Germany. In the next few minutes, I will present you our paper with the title Separated Allocator Metadata in Disaggregated In-Memory Databases, Friend or Foe. The paper was co-authored with Daniel Ritter, Martin Bussier, and Michael Perschat. In a research project collaborating with Seagate Technology, we investigate how disaggregated memory can be leveraged for in-memory databases. For this, we use the in-memory research database HiRISE, which has been developed by our research group. The aspects of interest in our research project are memory management mechanisms to efficiently store data on disaggregated memory and autonomous data placement algorithms. One part of this project, which our paper is about, is to investigate the performance impact of separating a memory allocator's metadata and application data on database workloads. For this, I will give you some background information. In-memory databases store most of their data in main memory to reach low latencies and high throughput during query processing. However, with the continuous trend of growing data, main memory becomes the limiting factor for such databases. Furthermore, in traditional data centers where a monolithic server is the base unit for scalability, different resource types such as compute and memory are co-located on one mainboard. This co-location of memory and compute limits their independent scalability, leading to resource over-provisioning. To overcome these challenges, a composable data center architecture will physically disaggregate traditional server resources into independent resource pools. In this architecture, an independent memory pool is referred to as disaggregated memory. Compared to DRAM that is co-located with CPUs on one mainboard, however, using disaggregated memory in an application results in higher data access latencies. In our case, this application is an in-memory database. Recent research shows that memory allocation significantly impacts the performance of modern database systems. In our work, we focus on memory allocation of an in-memory database system with disaggregated memory. More precisely, we studied the impact of separating a memory allocator's application data and metadata. Application data means data requested by the application, which is the database in our case. Metadata is data internally required by the allocator for organizing the memory. Such data contains, for example, information about allocated and free memory. With separating the data, we mean separated data placement. Usually, both application data and metadata is stored on the same kind of memory. In the shown figure, this scenario is illustrated in blue, where all data is stored on disaggregated memory. With disaggregated memory having a higher access latency compared to CPU local memory, we investigated whether storing metadata on CPU local DRAM while application data is stored on disaggregated memory has a positive performance impact. In the figure, this scenario is illustrated in green. We used the open source relational in-memory database management system HiRise, written in C++. It stores data in columnar layout, and each table is horizontally partitioned into chunks as shown in the figure on the right. Resulting column fractions stored in a chunk are called segments. Data is inserted into the most recent chunk, which is mutable. Using multi-version concurrency control, updates and deletes are executed by appending a new row and invalidating the previous version. Once a chunk reaches its limit, the chunk is marked as immutable and a new mutable chunk is appended to the table. Segments are the unit for data placement on different storage tiers in our work. In our experiments, we run a HiRise instance on a server that is connected to storage and memory as shown. The server is connected to an NVMe-based SSD and to a Gen Z-based block-level disaggregated memory appliance. The disaggregated memory appliance consists of a bridge, a switch, and memory modules which are all Gen Z-based. The bridge presents the appliance as an NVMe namespace and translates NVMe I/O to Gen Z memory transactions. It is connected to the switch, which connects the server with Gen Z memory modules. A look into the HiRise database shows you the data tiering plugin and a memory allocator. The tiering plugin is responsible for migrating segments from CPU local DRAM to the SSD and to disaggregated memory. As the memory allocator, we use the widely used open source memory allocator gmalloc. To store data on a block device, we map a file stored on the corresponding device into the database's virtual memory address space. Usually, this is achieved with the POSIX mmap system call. With mmap, however, memory mapped pages reside in the kernel's page cache, which is shared by multiple processes on the same machine and which size cannot be limited. To limit the page cache and to ensure that pages are evicted from the page cache to the specified block device, we use UMAP, a user space page management library. Due to time constraints, I cannot go into the details of the individual experiments, so I will give you a short overview of what we investigated. First, we measured the memory footprint of metadata compared to application data. For this, we used the data of the widely used analytical database benchmarks TPCH and TPCDS. Our measurements showed that the footprint is marginal with less than 0.5% compared to the application data. Second, we looked into a configuration parameter of the gmalloc allocator. By default, gmalloc does not discard unused virtual memory, but retains it for later reuse. This, however, results in using more virtual memory address space. We investigated the performance impact of disabling this option with the TPCH benchmark. Our results showed a significant impact on both the memory consumption and query processing latency. Third, we investigated the impact of different page sizes of the used page fault handling library UMAP using both the TPCH and TPCDS benchmark. The results showed that the UMAP page size has a huge impact on query runtime and has to be selected workload specific. Our main investigation aspects in this work were the performance impact of separating gmallocs metadata and application data. With performance impact, we refer to the execution time. For the analytical read-only database workloads of the TPCH and TPCDS workloads, we could not observe a significant improvement or decay. Furthermore, we investigated the impact on write-intensive workloads. For this, we used the data of the TPCH and TPCDS benchmark again and measured for each benchmark the impact of the data migration only without executing the individual benchmark workload. Data migration means the procedure of writing all table segments from main memory to the specified secondary storage device, which is the disaggregated memory appliance in our case. Also, this experiment did not show significant performance changes. In the previous experiments, we used our data placement approach in HiRise with gmalloc and UMAP. To reduce potential noise, we reduced our software and hardware stack in another experiment. Instead of storing the data on disaggregated memory, we stored it on a remote NUMA node. Similar to the previous experiments, we compared the resulting performance with all data on the remote NUMA node with the resulting performance when metadata is stored on the remote nodes and application data on the CPU local NUMA node. As a workload, we executed 10 million sequential allocations. In this setup, we identified a slight performance improvement. More details, such as the memory layout of the gmalloc memory allocator, an elaboration of our data tiering approach used in HiRise, and details about the different experiments and their evaluation results can be found in our paper. If you have further questions, please do not hesitate to contact us. Thank you for your time.
All right, and I hope we have further questions. Are there any?
I can ask a question. Again, sure. Congratulations, very good work. Can you talk a little bit more about the impact of the metadata sizes, whether you think it's representative of other application domains or the specific ones that you experimented with? Yeah.
Yeah, thank you for the question. With the metadata in this gmalloc allocator, we only observed very marginal shares compared to the application data, as I also mentioned in the talk. And actually, we did not look into other allocators, so I'm not sure if this is representative for allocators in general. So unfortunately, I can only speak for gmalloc, and for other applications that also use this allocator, this is definitely representable because this is an internal property of this allocator.
I have a question as well. You mentioned this data. You mentioned this data tiering component, right? That decides whether to move pages to SSD or to disaggregated memory. Can you please elaborate a bit on it? Like, which kind of policy did you use? Did you have to modify the way HiRise worked initially?
Yeah, sure. So to store data on different kinds of devices, especially on block devices, since we use a block level disaggregated memory device in our case, we used so-called polymorphic allocators. You can find these allocators in the standard library, the C++ standard library, and a polymorphic allocator is a stateful allocator, which internally stores memory resource. And the way we work now is that we specify our custom memory resource, give it as an attribute, as a parameter to this polymorphic allocator. And internally in our memory resource, we use this UMAP page fault handler so that we can avoid using the page cache of the OS, so that we have our application specific page cache. And for the memory mapping, we also use UMAP instead of mmap. So essentially with UMAP, we map the corresponding file of our disaggregated memory device into the memory space, and then we can use this address space for our data structures, such as std vectors or other data structures in C++.
Okay, so okay, I understand. And so whether an allocation ends up being hosted by the SSD or the disaggregated memory is based on what? Latency?
Okay.
Availability of.
We don't have any kinds of automation in that. So this is actually a manual decision which we did. So we also made some other experiments where we, for example, placed all of the segments, these small partitions in our high-rise database on disaggregated memory. But for this specific problem with the metadata separation, we placed all of the metadata in disaggregated memory. And to achieve that, there is an experimental feature in gmalloc which we used. So there were also some other users of that allocator that requested this feature, and it's in an experimental state. And we leveraged this feature of gmalloc to be able to store metadata on a different device and then the application data.
Okay, interesting. Thank you.
All right, so we have probably time for one last question. Okay, if not, then well, thank you, Marcel, for answering all the questions.
Sure.
All right, and let's go to the last video.
Hello, everyone.
Oh no, buffering.
Today, I'm going to be talking about composable infrastructures in an academic research environment, the lessons that we learned when implementing it, deploying it to our users, and also where we're going with it. My name is Lance Long. I'm a senior research programmer at the University of Illinois, Chicago, in the Electronic Visualization Lab, part of the Department of Computer Science. I design and develop novel instrumentation, innovative spaces, and applications with the faculty, graduate, undergraduate students, and staff. In the Electronic Visualization Lab, I maintain our cyber infrastructure, and that involves working with our testbeds, with external collaborators, and also engaging with industry in research and commercialization of the applications, the technologies, the instruments, and the spaces that we develop. The academic cyber infrastructure needs to be as diverse as the problems that the College of Engineering sees. So it is often a mixture of on-premise and partner clouds. And given that we're a data visualization lab with a long history in networking and virtual reality, we have a strong on-premise cyber infrastructure presence that can support a huge variety of workloads. Our collaborative nature and working with art and medicine and engineering provides us a perfect centralized location to deploy new cyber infrastructure. We see a growing demand among our faculty for GPU resources on campus. And so the research includes deep learning, but also visualization and a combination of those two. We're seeing a demand for different deployment types. We used to do a lot of bare metal servers that were custom configured, and now we're seeing a lot of multi-tenant orchestrations. We still have a lot of bare metal. People are interested a lot more in the analytics of their application and how it's running. And then also, obviously, containers, the AI and machine learning containers that come from NVIDIA. I mentioned traditionally, we've always looked towards the server architecture. And so Modern unified AI infrastructures like the NVIDIA DGX are really fantastic solutions and support a lot of our demands, but they're extremely costly. They're very over-provisioned. Like I said, we have this huge adjustable scale of requirements that the users need. And then they're not very scalable. So if we need to add more resources, we have to buy another one of those units. And then also a lot of our faculty have specific requirements for alternative accelerators. So maybe they're doing FPGAs or they're doing DPUs. And so implementing those would require a separate server from a unified solution like this. So what we sort of settled on was composable infrastructure, right? Composable disaggregated infrastructure, CDI, where the resources can be abstracted and they can be managed by software. This implementation obviously is built on a PCI Express switch. This is the one from Liquid. And so you have each of the elements that are separate. So the GPU chassis or the NVMe chassis or the network chassis. And they're all connected by that core PCI Express switch to the compute nodes. And all of that is dynamic and adjustable. The composable solution has a few obvious benefits for us. There's some long-term cost benefits. It provides immediate access to resources for a lot of our users. It still provides us our reproducibility and portability platform that we need. And it has additional security and scalability features that we really like. A brief timeline, in 2016, we were introduced to composable disaggregated infrastructure. Since then, we've acquired a development system, purchased and installed our new 2-rack system, provided a number of users that continues to grow, and have completed a more recent expansion of the system to provide even more benefits going forward. So this is our COMPSYS DLV system. This is our composable infrastructure that we deployed. It's 2 racks, 24 compute nodes, 1,200 gigabit per second networking cards, 153 terabytes of storage, 32 NVIDIA V100 GPUs, 32 T4 GPUs from NVIDIA, and then also 4 additional 100 gigabit NICs that are composable so that we can move them between the different nodes. Composable infrastructure. In general, it breaks down the essence of a server. So all of the elements that are generally needed to create one of these GPU servers for users, the compute, the GPU, the storage, and the networking, are taken from this pool of resources and combined into a single server that is identified for the user or that is identified for the Kubernetes pool that we're looking at. And so we can uniquely configure and size each of these servers to the application or to our container workload that we're expecting. Or even to run multiple applications simultaneously. If some users need CPUs and others need GPUs, right, we can co-locate those users on the one server. The COMPSYS DLV instrument has shown to be highly flexible, able to change the infrastructure and its resources on the fly based on an application's requirements. It's scalable, so we can add additional infrastructure as needed, or adjust what's given to a specific node based on an application's needs. And so I mentioned that we can control the infrastructure using software. There is a traditional interface that Liquid provides, which is your standard UI, which allows you to create the nodes, create groups of nodes, create groups of resources and deploy it. But we've taken that a step further and we've actually created our own API, which allows us to sit on top of their API and use Jupyter notebooks to redesign our nodes or to recreate our pools of resources on each node. And so this way we don't have to go into a UI and point and click and add things. We can do it all programmatically and we can do it all reproducible. So if a system goes down or a user says, hey, can you give me this? I can just run everything I need in a Jupyter notebook instead of having to log into a separate UI. This system provides a way for student researchers to easily handle their workload diversity and supports modern workflows that they're interested in. Given the limited funding that is often available for academic resources, this provides a solution to our over-provisioned systems and reduces the support and administration required. On COMPSYS, we now manage workloads using Metal as a Service for the operating system layer, Kubernetes to deploy and orchestrate the containers and a variety of its supporting services, Docker containers to run user applications using NVIDIA Catalog Dockers, Docker Hub, or even private registries that we host locally. And then Jupyter Lab for a web-based development environment for our users. Users can deploy their applications using Kubernetes pods and then launch Jupyter Lab notebooks from inside their containers running directly in COMPSYS. Users could also use an instance in Jupyter Hub on the front end to manage all of their data and as a secure web-based portal to running their applications. What we're looking at now is composable co-location, right? So now that we have all these chassis and these different switches and compute nodes, we can have users bring their individual accelerators or just purchase individual accelerators. So new faculty or faculty that have a specific project need that maybe they just need one GPU instead of buying their own server that their user has to administrate, they can just buy the accelerator that they need, stick it into our composable infrastructure, and then we can link that to an existing compute node. If they need more compute nodes, they can add that to the system, and then that way they have access to the larger pool of resources. And so it allows the infrastructure to scale as the department grows or as the research grows, as the demands go, much more quickly than traditional models. We installed this in 2020, which was right at the start of the pandemic when all of our work went remote. And so using this type of system, we were just able to support all of our workload variability in our applications remotely. We implemented all of these resources with one full-time employee and one undergraduate student. And so now we did all of that in the middle of the pandemic, something that we wouldn't have been able to do with our traditional servers. So in conclusion, we have found that composable infrastructure enables our academic researchers to accelerate the pace of their research by providing them with an on-premise centralized resource. It allows them the ability to quickly deploy bare metal or containers that are appropriately sized as their application or as their research demands. And so COMPSYS has shown to be a cost-effective, mid-scale, agile resource for the College of Engineering. It's been able to serve as an on-ramp for users to develop their software before scaling to larger cloud or HPC environments. And it's been a great tool for supporting our uneven applications and the modern workflows that are needed in an academic environment. And now with composable co-location, the faculty can just bring the accelerators or other devices that they need and install them in this type of system without having to maintain a separate device. And so the COMPSYS DLV system, the 2-rack composable infrastructure that we installed, seems to be the appropriate size for a multi-department college. So COMPSYS using Kubernetes and Jupyter Notebooks has enabled faculty and student researchers to sort of more quickly come to task. It's eliminated a lot of the system support and maintenance that's often required by our student researchers. And then using containers, multiple researchers can work on the same application in parallel. And then, of course, the skills that are learned by using these types of hardware as it emerges and how to scale their applications faster and the different types of technologies they can employ. With that knowledge, they're able to directly transfer to the emerging industry problems. So that's what we've been doing with our composable infrastructure in an academic research environment. My name is Lance Long. Feel free to reach out if you have any questions. Thank you.
All right, so are there any questions?
I have two actually. Well, one.
Go. Sure, go ahead.
So the first one would be, what was the main model that people were using this system for? Is it like the users run something, release all the resources, and get you reconfigure for the new user, or there were also users asking for just add one more GPU, add 2 GPUs to this existing configuration?
So the benefit of a system like this is it actually allows sort of both. So we have users that maybe they want to reproduce their research for a paper publication that they're looking at. And so they'll request like the resources, a specific set of resources for a specific set of time. Other users will run their applications and then release it as they're developing software. And then other applications, like maybe they are just learning to scale it. So they'll say, hey, can we have one more GPU? Or now we're in this phase, can we have a different type of GPU? Or can we have 8 GPUs? So it just really allows us the flexibility to address a huge variety of different problems and pretty much any request that the users can make on, obviously, the number of GPUs that they make can't exceed what we have, but so far we've been able to handle all the variability.
Okay, yeah, that's actually interesting. And then the second question is basically related to this. You say you use Kubernetes for orchestrating your workloads. How are these two things, like the composable hardware and Kubernetes, interfaced with each other? Is Kubernetes aware of the possibility of getting some more hardware, or you just reconfigure a node and add it as a new node in the cluster? How do you interface?
So currently, if we use Metal as a service, so when a node is generated, it is automatically added into the Kubernetes system to be made aware. But when we alter the number of GPUs, we just have to restart the Kubernetes client. So that can be sort of programmatically scripted to restart. And then it will re-find all of the new GPUs. So we do have to bring like that node's awareness down for a minute while we restart the Kubernetes service. We did apply for a grant that was denied, which would allow us to do better integration. So you saw we did some development of our own to allow users or allow me to adjust the resources using Jupyter Notebooks. And so the grant we had looked to get would have added that functionality directly into Kubernetes. And these manufacturers that are building the composable infrastructures already have integrations for things like Slurm for scheduling. Mm-hmm. So I would expect within another year or two, we'll see similar integrations to software like Kubernetes.
Yeah, that would be actually very interesting, right?
Right.
Okay, thank you.
Sure thing. Thank you.
All right, I think we can have a last question. Okay, so I will ask the last question. And that is, you mentioned in your presentation that you also have those NVIDIA DJX systems. So I was wondering, have you done some performance comparisons? I mean, I could imagine that, you know, the PCIe switch adds latency. So, you know, is there a performance difference between those two systems?
So we don't actually have the DGXs because they're a bit out of our price range. That was our comparable. So if we couldn't, if we wouldn't have been able to purchase composable, then we would have had to try to get something like a DGX. We do standard over provision servers, let's say. So it's just a super micro chassis filled with GPUs and networking and stuff traditionally. So we haven't done any performance testing with the DGX. But the PCI Express does add latency. The more switches, obviously, you've added. But in just sort of basic tests, we found that in a standard server, super micro chassis, the latency through one switch is very similar. But obviously, the more switches you add, and I think it was mentioned earlier, right? The more you go beyond a rack, the more latency you're going to introduce into PCI Express. And then you'll have timing issues if you go wide area, et cetera, et cetera.
And it depends a bit on the application too. A lot of workload for machine learning are not super sensitive to PCI Express communication. They do a lot of compute and then return a result. It depends on some other application, more like the physics application where it's more compute intensive, might be more sensitive, or data transfer.
Yeah, we do a lot of real-time graphics here also. And so Luke brings up the point is that your expansion chassis is only connected at, say, 1x16 lane or 2x16 lanes, but you'll have 8 to 10 GPUs in there. So if you're trying to interconnect those, you're going to hit latency pretty quickly for a real-time application. So they're really good for AI and machine learning workloads, but for real-time workloads, you would have to design the system specifically with those latencies in mind.
All right, thank you. Interesting. Good. Then, thank you again for answering all the questions.
Thanks for having us.
And I think then we'll have a short break.